Hello, everyone. So this is the second part of lecture 29, where we will discuss about peak runoff. So we discussed a little bit about peak runoff. So this is the maximum rate of discharge during the period of runoff caused by a storm is called a peak runoff. So we also discussed a little bit about this graph, which is called the hydrograph. So you can see initially there is no runoff because soil is absorbing all the water. And with time, the runoff is increasing. And at one point, it will reach at the peak flow. So that point or that magnitude, this one, that is actually called the peak runoff. And by the time it reaches at that point, that time is actually the time of concentration. So we already know that at the time of concentration, peak runoff will happen. So for peak runoff, there are few factors like which will influence. They can be divided into two broad categories. One is the watershed characteristics, and the next one is storm characteristics. So for watershed characteristics, it can be size of the watershed, either it's large or small area. Obviously from small area, we will have a small runoff. And the geology of a watershed, the initial moisture content, types of soil. If the soil is already in high moisture content, obviously it can't take too much water. So majority of rainfall will flow as runoff. So for that type of watershed, obviously we can expect more runoff. And the geographical location of watershed, either it's hilly or flat area. So for hilly area, due to slope, maybe we will get more runoff. The next one is the orientation of watershed with respect to storm pattern. So if that is the watershed and if that is the storm pattern, so obviously the whole storm is like within the watershed, so we will get more runoff. But if you look at this one, so at least half of the storm it's actually happening outside of the watershed, so we will get less runoff here. And the very last one, and that is very important one, which is the type of covers or vegetal covers. So if we have grass and small bushes in the watershed, obviously that will obstruct the runoff and will reduce the peak flow. And if we have the impervious cover, like there is no soil, it's kind of like urban area or something, so there will be no place where water can go. Almost all of the water will run as a runoff, so impervious cover will increase the peak runoff. The next one, the storm characteristics. So obviously intensity and duration, those are very important. Intensity of rainfall or storm. If the intensity is very high, obviously we will get more runoff. The duration of storm lasts for longer or shorter period. If it lasts for longer period, we will get more runoff. The distribution pattern of a storm, we already discussed that. And the very last one is the storm direction. So if that is the outlet and the storm direction is in that way, obviously with time we will get more flow or more runoff here. But if the water flow is going this way, but the storm direction is on the other way, we will actually get less peak flow. Okay. So why we are concerned about the peak runoff, like why we need to know what will be the peak runoff from a watershed. The first reason, if the runoff is very high, obviously it will create a flood, and we don't want that. There are some other reason also, like if we want to prevent the flood, and for that if we want to create some hydraulic structures across the river, obviously we need to know the peak runoff, or that will be the design runoff. And for carrying the water of this runoff through the storm sewer, we have to design that. So we need actually a design flow. So this peak runoff can be the design flow for that storm sewer. So basically for these reasons, we need to know what will be the peak runoff from one watershed. So now we know why we need to estimate the peak runoff. There are some widely used methods. Using those, we can actually calculate the peak runoff. The first one, which is very widely used and very easy, which is the rational method. The second one is National Resources Conservation Services, NRCS, or Technical Report 55 method. And the last one is hydrograph method. So for rest of this course, we will actually discuss these three methods. So the very first one, the rational method, maybe you already know about this one from your transportation class, where you have to find the drainage water amount or something. So this method was developed about 100 years ago to predict the peak runoff for small urban watershed. So look at these two words, small and urban watersheds, okay? And when this method was developed, they used two assumptions. The first one is rainfall occurs at uniform intensity for a duration at least equal to the time of concentration of the watershed. And the second one is rainfall occurs at a uniform intensity over the entire area of the watershed. And you can imagine these two assumptions, maybe it's not true always, because maybe we don't have the uniform intensity over the entire area or uniform intensity for the whole time. So that's why this method, that is not a good method for a big watershed. And this method is a valid method for urban watersheds up to 50 acres. So that is kind of small area. And the equation for rational method is CIA, and that C is actually the dimensionless runoff coefficient, which will take care of like the watershed characteristics, like geology, geographical location, or the vegetal cover. I is the intensity. So intensity means the amount of water per unit time. So it can be inch per hour, it can be feet per second, or it can be inch per second, something like that. And the area is the total area of the watershed. Okay. And this is the table for the runoff coefficient. As I said, it will take care, like the type of the surface of water surface will actually reflect on this C value. If you look at here, like the lawn heavy soil or lawn sandy soil, and if you look at the slope, if the slope is less than 2%, you are getting the C value 0.13 to 0.17. But when it's very high or very steep, you can get 0.23 to 0.35. Okay. For asphalt paving, the C can be 0.7 to 0.9. At the same time, if you look at park, like cemeteries, like where you don't have that much impervious area, you can get the C value only from 0.1 to 0.3. And for rural catchment, it can be different type of C value. We will use that. So I just wanted to make sure that you understand how the C value will reflect the type of watershed characteristics we have. So once we know that, obviously we will do one class example for estimation of peak runoff using the rational method. I uploaded a blank copy of this one on Canvas. Please download that and work on that. So let's read the question first. An urban watershed in Bridgewater, Connecticut is shown below, along with the travel paths from the most remote point in each sub area. Okay, so the detail of the sub area are given in the table here, like what type of surface and the travel time. Using the attached intensity, duration, frequency or IDF curve for this site, determine the 20-year peak flow at the drainage outlet at G. So this is the whole watershed, and G is the outlet. So they are asking you to find what will be the total amount of, or the peak runoff for this area if the storm characteristics or the frequency of storm is 20 year. Like every 20 year, the possibility of happening this amount of storm is like kind of 100%. That is the 20-year peak flow. Okay, so they also give that 1 acre equals to 43,560 feet square. Okay, so for C, we already know for rational method, the equation is Q is equals to CIA. So for C, we will use this table, and for I, we will use this IDF curve, and for A, that is already given, so we can find the A from there. So let's start to solve this problem. So estimation of peak runoff. The first one is sandy soil steep. So here is the sandy soil, and that is the steepest one. Now, for finding C, an engineer, he or she can use the C values based on their experience or from field inspection, something like that. Since we don't have a field inspection opportunity here, so what we will do, we will take the maximum value of C so that we can get the maximum runoff, which is the worst case, and we can design our structure based on the worst case scenario. Okay, so for sandy soil and the steep, the range is from 0.15 to 0.2. So we can take 0.2. For playground, there is no direct playground here, but we can use the parks as a playground. So the maximum value is 0.3. The asphalt paved, we have direct asphalt paving. The maximum value for C is 0.9. And the industrial building roof, so we have roof and industrial, like industrial as well, and for both of these cases we have 0.9 as extra. So the maximum value for C, we can get 1, and if you look at these two, we are having 0.9, 0.9. So basically the runoff is very high in these two type of surface, because obviously there is not enough space where water can go, so most of the water actually runs as runoff. Okay, so now we have different C for different area. There is one way we can calculate the peak runoff for each area, but in that case we need to know the intensity for each area, which we don't have right now. We have a common intensity curve here, so we can't calculate the individual runoff. So what we will do, we will find a common C for this whole area, and we will use the weighted average. Okay, so the weighted average or combined C is like the summation of CA divided by A. So finally we will have 1C, which is 0.568. So once we have the C, now we need to find the I. So this is the curve that is called intensity, duration, frequency curve, will be used for determining the I. So if you look at here, the duration, and the intensity is on y-axis. So this duration is actually the time of concentration. So we need to know the time of concentration, and you are seeing some of the frequency line 150, 20, 10, 5. So for our case, we have to use 20-year frequency. So once we know the time of concentration, we can get the rainfall intensity. The reason this curve is called the idea for intensity duration frequency curve, that's because that is the intensity I, that is the duration D, and those are the frequency. And for each area, they actually develop intensity duration frequency curve. So based on the area, we can have different type of IDF curve. So as we just saw that we need to know the time of concentration, and we already know time of concentration is actually the maximum time water will take to come to the outlet from the farthest point. Now we have 1, 2, 3, 4 areas, and for each sub area we have some travel time, you can see here. So at first we have to find what are the possible paths for the time of concentration, and then we will find the maximum time, and that will be the time of concentration. Now you may have one question, why don't we are calculating the time of concentration as sheet flow, shallow concentrated flow, and the open channel flow? That's because they already gave us the travel time, so we don't need to calculate those time individually. Okay, so possible paths for TC, the first one is this one, like BF to FG, 23.9 minutes. The next one is DF to FG, 17.3 minutes. The next one is CEEFFG, like from this point to this point, 26.2 minutes. And the last one is from A to G, which is AEEFFG, which is 27.2 minutes. So out of these four, obviously 27.2 minutes is the highest one. So that is the time of concentration for this whole watershed. Now we know the time of concentration, which is 27.2, and we know the frequency, which is 20-year. So we can get the rainfall intensity here, which is 4.8 inch per hour. So now we have C and we have I, so we can calculate the peak runoff. So C is 0.568, I, it was in inch per hour. If I want to convert into standard unit, feet per second, that is the number. And the area of watershed, 46.1 acre. And if I multiply with the conversion factor, I will get this number. So basically I'm getting 126.73 cubic feet per second. That is kind of large flow. And if you notice, the area that is actually less than 50 acres, so we can actually use the rational method. Now I will show you one thing. Here I converted the I and area into the standard unit, but if I keep those in their original unit, still I'm getting 125.68, which is pretty close, right? That's because the conversion factor from like inch per hour multiplied with acre to feet per second multiplied with square feet is 1.008. So if you have I is in inch per hour and area is in acre, you can actually skip all of this conversion and you can directly use that I and A values in that equation to find the total runoff in CFS. So that is the end of your class example 21. Please download the empty question and work on that. And if you have any question, just let me know. Thank you.